What happens inside a black hole? This is one of the greatest mysteries of the cosmos. A place where space, time, and the very laws of physics seem to collapse into something we cannot yet understand. In this extended exploration, guided by AI simulation and human imagination, we will dive deep into what might happen if we could journey beyond the event horizon of a black hole. Part 1: The birth of a black hole. To understand what lies inside, we must begin with how a black hole is born. Black holes are not random monsters scattered across the universe. They are formed through natural processes, often from the death of massive stars. When a star many times heavier than our Sun exhausts its fuel, it can no longer support itself against the crushing force of gravity. Its outer layers explode outward in a supernova, one of the brightest events in the universe, while the core collapses inward. The matter is crushed into an incredibly dense point, creating what we call a singularity. The gravity of this singularity is so extreme that it warps space-time itself. Around it forms the event horizon, the boundary where the escape velocity is greater than the speed of light. Anything that passes this invisible surface, whether matter or light, cannot escape. Black holes vary in size. Some are just a few kilometers across, formed from collapsed stars. Others, called supermassive black holes, sit at the centers of galaxies, containing the mass of millions or even billions of suns. The one at the center of our own Milky Way is called Sagittarius A, and astronomers have even captured an image of its shadow using the Event Horizon Telescope. Part 2: Approaching the monster. Now, imagine yourself as an astronaut, daring enough to approach one of these cosmic giants. From far away, the black hole looks stark and unremarkable, but its influence on space is obvious. Stars orbit faster, gas clouds spiral into glowing disks, and jets of radiation shoot across space. As you get closer, you encounter the accretion disk, a swirling ring of superheated gas and dust falling toward the black hole. Temperatures here rise to millions of degrees, releasing X-rays that we can detect from Earth. This region is deadly, but it is also beautiful, a cosmic whirlpool of light spiraling into darkness. Time itself begins to change for you as you approach. Einstein's theory of relativity tells us that gravity bends time. Near the event horizon, time for you moves normally, but for distant observers, your clock ticks slower and slower. They would see you approach the horizon and then appear to freeze forever at its edge, fading slowly into red light. This phenomenon is called gravitational time dilation. It means that black holes are not just destroyers of matter, but manipulators of time itself. Part 3: Crossing the event horizon. No matter how powerful your engines, no matter how strong your will, escape is impossible. You are on a one-way trip to the singularity. From the outside universe, you are gone forever. No signal, no light, no information can leave. This makes black holes not only fascinating, but deeply frustrating for scientists. We can only speculate what happens inside, because by definition, no data escapes. Part 4: Spaghettification, the stretching of matter. The first major effect you would feel is tidal gravity. The pull of the black hole on your feet is stronger than on your head. This difference in force stretches your body violently, a process scientists call spaghettification. At first, it might feel like your body is simply being pulled, but as you get closer to the singularity, the stretching becomes extreme. Molecules tear apart, atoms separate, and even subatomic particles may be ripped asunder. You are transformed into a thin stream of matter, stretched across space like spaghetti. It sounds terrifying, and it is, but it is also a demonstration of just how powerful gravity can become when concentrated into such a small space. Part 5: The singularity, the great unknown. At the very center of the black hole lies the singularity, the ultimate mystery. This is a point of infinite density, where the curvature of space-time becomes infinite. Here, all known laws of physics break down. General relativity, Einstein's great theory, works perfectly to describe how gravity operates on large scales. Quantum mechanics, the theory of the very small, explains particles and atoms, but at the singularity, these two pillars of physics clash. Relativity predicts infinite density. Quantum mechanics says such infinities are impossible. The truth is we don't know what happens. Some physicists believe that the singularity does not truly exist, but that it is a sign our theories are incomplete. Perhaps a theory of quantum gravity, uniting relativity and quantum mechanics, will one day reveal the true nature of black holes. Until then, the singularity remains hidden, not only by distance, but by the laws of the universe itself. Part 6 Exotic Theories Wormholes and White Holes. Because black holes push our science to the breaking point, many exotic theories have been proposed. One idea is that black holes might connect to other regions of space through tunnels called wormholes. If true, entering a black hole could mean emerging somewhere else, or even in another universe entirely. Science fiction has embraced this idea, imagining black holes as gateways to distant galaxies or parallel worlds. But in reality, wormholes are purely theoretical, and even if they exist, they might be unstable, collapsing instantly. Another idea is the existence of white holes, the opposite of black holes. Instead of trapping everything, a white hole would eject matter and light, never allowing anything to enter. Some speculate that a black hole in one universe might be a white hole in another, connected through a wormhole. It is a fascinating thought, but again, no evidence exists. Part 7 Hawking Radiation, the slow death of a black hole. For a long time, scientists thought black holes lasted forever, but in the 1970s, Stephen Hawking proposed something revolutionary. Through quantum effects near the event horizon, black holes emit tiny amounts of radiation. This is now called Hawking radiation. Over time, this radiation causes the black hole to lose mass. For small black holes, this process is relatively fast. For supermassive black holes, it takes trillions upon trillions of years, but eventually, even the largest black hole will evaporate and vanish. This discovery was profound. It showed that black holes are not eternal prisons, but objects that live and die like stars. It also created new puzzles. If black holes evaporate, what happens to the information about everything that fell inside? Does it vanish forever, or does the universe somehow preserve it? This is known as the black hole information paradox, and it remains one of the biggest questions in modern physics. Part 8 The Human Perspective. So let's return to you, the astronaut. From your point of view, once you cross the horizon, your fate is sealed. You fall inward, stretch thinner and thinner, until you meet the singularity. For you, the journey is short, but for the outside universe, you are frozen at the edge, forever unreachable. This paradox shows us that reality is not always absolute. Different observers can experience different versions of truth, and both can be valid. Black holes force us to rethink what we mean by time, by space, and even by existence. Part 9 Why Black Holes Matter. You might ask, why should we care? If black holes are so far away, why do they matter to us? The answer is simple. Black holes are keys to the universe. They shape galaxies, drive cosmic evolution, and may hold the secrets to unifying physics. Studying them teaches us about gravity, about time, and about the ultimate fate of matter and energy. Without black holes, the universe as we know it would not exist. And beyond science, black holes capture our imagination. They are symbols of mystery, of power, of the unknown. They remind us that the universe is far stranger than we can imagine. Part 10 The Final Question. So, what really happens inside a black hole? Do we face destruction, spaghettification, and the crushing singularity? Or is there a doorway to other worlds, hidden beyond our reach? The honest answer is we don't know. Perhaps in the future, new discoveries will reveal the truth. Until then, black holes remain the universe's greatest mystery, a challenge to our understanding, and a reminder of how much more there is to learn. What do you think? Are black holes cosmic monsters, or gateways to new realities? Let us know your thoughts in the comments, and don't forget to subscribe for more AI journeys into the greatest mysteries of space and time.